Okay. And yeah, let's start. And the midterm review class is very important. Yeah, you need to think that. Yeah. Okay. And yeah, let's start this class. Yeah. Today we will focus on Fourier transform for periodics. Actually, yeah. Before we talk about this class, like we talk about like how to represent the signals, periodic signals in frequency domain. What's the name for that? Do you remember? Yeah. Like how to represent, how to like do a frequency domain representation for the periodic signals. Yeah, we use some tool or some representation. What's the name for chapter 3? Fourier series, yeah. You just, like we just learn Fourier series and to do the kind of like a frequency domain representation for periodic signals. But I don't know if have you ever heard like Fourier series before? Actually, usually we just talk about Fourier transform. Am I right? Like when you have some class, engineering class or some class, we usually focus on the Fourier transform. We seldomly talk about the Fourier series. That's today's class is just like the reason why we always talk about Fourier transform, even for the periodic signals or non-periodic signals. Because last class we talk about the Fourier transform focus on the non-periodic signal, am I right? But the Fourier transform also can be used for the periodic signals. And why we want to use the Fourier transform for the periodic signals? Can you guess? Can you guess? Let me see if major frequency, yeah. But like usually we talk about one signal. We just want just one tool to deal with it. Am I right? We don't want two different tools. Like we need to find out this is a periodic. We use the Fourier series. This is a non-periodic. We use the Fourier transform. Usually, we just want to use one tool. Yeah. So that's the reason why we want to use Fourier transform for periodic signals because the Fourier transform can be used for the non-periodic signal. If the Fourier transform also can be used for the non-periodic signal, which means we only need to remember the Fourier transform thing. We don't need to like remember FS like a Fourier series thing. Am I right? That means that we like one tool. We don't like two tools. Am I right? Yeah, that's the reason. Okay. So today's goal is firstly we will try to review the CT CT Fourier transform for signals and impulse response for LIT system. And then we will try to study a few often used FT pairs. Actually, when we talk about the F series FS, FS for periodic signal, we also learn two very often used FS pairs, am I right? Yeah, here we will also study a few very often used FT pairs. And the purpose is just to simplify, to compute the FT of non-periodic and periodic signals. Yeah, and today because we will talk about the periodic signals, so we will focus on the periodic signals. But the why we want to learn the very often used FT pairs because it can help us to simplify the computation for the FT coefficient or synthesis thing. Yeah, similar thing. Yeah. Okay. Let's try to review the FT Fourier transform. Yeah. Before we review Fourier transform, let's review the FS. Yeah. We talk about the FS synthesis and analysis. This is synthesis, which means your signal actually you can represent it in frequency domain because this is just the specific one key fixed, for example, 1, 2, 3, which means you have the specific frequency, because this is fundamental frequency, omega naught is fundamental frequency, right? Different key, which means your signals has different frequency component. That makes sense to you? Yeah. The EG cap now doesn't have cap. EG omega naught T is just a fundamental frequency, fundamental like a atom thing. The key is just like a different different frequency. And the AK we know it's related to magnitude and the phase, right? When you phase shift. Yeah, which means this is just the kind of like signals, periodic signals in a flux domain representation. Yeah, we know that, right? And AK, yeah, we use this equation. We call it as analysis. Yeah, this AK, which means for the different key, and the AK just relates to the magnitude and the phase shift. For different key, which means for different frequency, what's your magnitude and what's your phase shift? That makes sense to you? Yeah, this is the FS synthesis and analysis. And then the FT actually is very similar, but it's specific for the non-periodic signals. And also the system frequency response from the impulse, from the response, which means the F Fourier transfer specific for two different kind of signals. One is non-periodic signals. The other is the system frequency response from impulse response. Yeah, but the FT and the FS actually it has similar idea. Yeah, you can see this is the FT synthesis equation, which means the signals, the non-periodic signals, can use this synthesis equation to represent it. Yeah, this is just like that because non-periodic signals, which means for the periodic signals, you can find the specific frequency, right? Harmonic frequency. Yeah, from K from 0 to 1, 2, 3, 4, like 0, negative 1, negative 1, negative 2, negative 3. You can find the specific frequency for the periodic signal. But for the non-periodic signal, since you cannot find the specific frequency, so what do you need to do? You just try to find all the frequency. Yeah, you can see here the variable is just a different frequency, right? You just try to traverse all the frequency to see which frequency will be included to this signal, and then put it there. That makes sense to you? Yeah. And then for this is just like compare the FS synthesis and the FT synthesis. It's similar because for the FS, the key is just an integer number, right? But here, because the frequency you don't know which frequency, so it will be the integer, and then the summation will change to the integral. Yeah, that makes sense to you. And then the K omega now, because for the periodic signal, you know the specific frequency, right? But for the non-periodic signal, you don't know it. This one is just a variable. Yeah, which means the omega naught, for example, is pi over 3 T, which means the component will be pi over 3, 2 pi over 3, 3 pi over 3. Yeah, but omega, it will be not fixed, right? Maybe it is pi over 3, pi over 4. Maybe it is 0.9 pi, like that. That makes sense to you? Yeah. And then this like coefficient, it is AK, which means it's just like for when we talk about the FS coefficient, do you notice the AK, when the key is fixed, it's a complex number, right? It may be the 1, it may be the G, it may be 1 plus G, or like that, right? It is fixed, but here the coefficient actually is not like it is a function related to the omega, which means I will go through all the frequency and find out how this frequency related to the signal. Yeah, it will be the function. That makes sense to you? Yeah. And then for the FT, like analysis, the FT coefficient will using this equation to represent it. Yeah, you can see the compare with this one and this one. For the periodic signal, we know what's the periodic for this signal, am I right? Period for this signal. But for non-periodic, the period is just all the range, am I right? From negative infinity to the positive infinity, am I right? That makes sense to you? And the x here, yeah, is the same thing, yeah, just the signal. And this here, P omega now, you use this P omega now with omega, because here it will now be a specific frequency. That makes sense to you? Yeah. Compare this one and this one. Any question? Yeah, actually the FT and the FS has a similar idea, similar theory, but we know like the periodic signal, you can use harmonic like a frequency. For example, our voice, flute voice, piano. It generated from the harmonic signal, frequency signal. Am I right? Yeah, usually it will have a specific frequency, but for the non-periodic, yeah, it will now like generated from the specific frequency. Yeah, this frequency doesn't have rule. That makes sense to you? Yeah. Okay. And then let's review the FT coefficient. Yeah. Here, the FT coefficient, we know it's a function related to the omega, am I right? And omega is the frequency, am I right? And it's a complex number. It's a complex function like that. Yeah, it's not a real function. And for the complex function, yeah, it will have the real part. It will have the imaginary part. That makes sense to you? Yeah, this is just the general form to represent a complex signal, complex function. That makes sense to you? Yeah. And for this one, we know like for any complex signal or number, we can like use this equation to represent the magnitude. Yeah, this is when you learn some complex numbers thing, you will know that. And then we call it magnitude spectrum. Yeah, because you can see as a frequency change, your magnitude will be changed, but that makes sense to you. So that's the reason why we call it spectrum. Spectrum, which means it is a range, am I right? Yeah. So this is just a power distribution over all frequencies, which means when your signal has a very strong relationship with the for example pi over 3, which means when your omega equal pi over 3, and this magnitude value will be large. That makes sense to you? And when your omega equal like pi over -5, and you will find if you find the magnitude is very small, which means when the frequency is pi over -5, and it will have a slightly relationship. That makes sense to you? Yeah, it will. It is the magnitude spectrum. Okay. And then for the freeze, yeah, like you can for all the like complex number or function, you can try to find the angle using this equation. Yeah, you know, like what does this mean? Yeah, we know like if you want to represent a complex number or complex signals, you will use the polar representation. Do you remember that polar? Yeah, you just use the angle and the magnitude to represent all the complex number. Yeah, this is just two different factor. This is magnitude and this is angle. That makes sense to you. And this angle you can like calculate using this equation. Yeah. Okay. And then we call it phase spectrum. Yeah. Why we call it spectrum? Because you can see the omega is different. The phrase will be different. That makes sense to you. So which means your phrase will have a range. It's not a specific value. That makes sense to you. For the fs, you can say fs from fs magnitude ek. You can say it's kind of like a discrete number value, right? But for the non-periodic signal, it seems a continuous value. That makes sense to you? Yeah, as the omega change. That makes sense to you? Yeah. Any question? Okay. And then, yeah, our like FT coefficient can be also represented by this equation. Yeah, this is the magnitude, and this is just the like breeze. Yeah, that means this is just a polar representation. Yeah, okay. And if you draw your like this part, you will find it's similar like this shape. If you draw your like freeze, you will find it will have this shape. And we know, yeah, there is a question: what is the freeze spectrum of a real FT function? Yeah, for the freeze spectrum. Yeah, what is a freeze spectrum of a real FT function? It is odd or even. For this one, it is odd or even. Yeah. Huh? Yeah, it will be the odd function of frequency, because you can see they will like if it is even, which means it will like symmetric along this axis. Am I right? Yeah. So here it will symmetric based on this point. It will be odd. Okay. And then let's try to review like the frequency response for different filters. Yeah, we know like why we want to learn why we want to analyze the signals in frequency domain. Because you can see if we know the frequency domain representation for these signals, we can easily to find a different frequency. Am I right? And then if we want to specific frequency for this signal, for example, my voice you think is too high, and you want to remove the high frequency signal and save the low frequency, and you just need to remove the high frequency part. Am I right? That's the reason why like we want to do like a frequency domain representation for signal. And you can see here, when we talk about the filters, it's always related to the frequency. Yeah, usually this is just like a frequency response. Yeah, why we call it frequency response? Because yeah, HT usually when we talk about the response, impulse response in chapter 2, yeah, we know what is HT. Do you remember? Yeah, we know like the delta T is impulse response. Am I right? Yeah, delta T is impulse response, and usually if delta T as an input go to a system, and then the output we will call it HT. That means that we will define it HT, and we will call it impulse response. Am I right? Yeah, for this HT, when we talk about it in chapter 2, this is just we try to represent it in frequency domain. Am I right? But in time domain, so it's related to T. Am I right? Here we just want to try to find the frequency domain representation for this like a response. Yeah, we will try to use this one. Yeah, because you can see if you try to like find this one, if you want to represent these signals in this form, firstly you need to find this one. Am I right? You need to find this coefficient, FT coefficient, and this one is kind of the H is kind of this part. That makes sense. It will use this equation. Am I right? And this xt here is just ht. That makes sense to you? Yeah. And then we just try to find this equation. And actually, this equation, yeah, it includes two different parts: the frequency, the magnitude, and the freeze. Am I right? And also, it will relate to different frequency. That makes sense to you? Which frequency will take up will have a strong relationship, which will have a slight relationship. Yeah, and then you can see different if your magnitude, if from here to here, from here to here, which means what kind of filter it is? Yeah, low. low pass filter because it will let the low frequency signal. This one, you can see this one. Actually, we call it frequency response, am I right? Actually, for the FT representation, it's just the coefficient, am I right? That makes sense to you? And this coefficient, which means I will apply this to different frequency, am I right? And if since the other part is 0, which means for this frequency, if I multiple this complete, which means it is 0. That makes sense to you? That makes sense to you? Yeah, only this part, it has a value. And then we will see, it has value, am I right? I will keep this complete, am I right? This atom, that means this specific frequency. That makes sense to you? Yeah. Similar with this one, this is also a low frequency because it relates to low frequency. Yeah, and this one, because I just want this part and this part, it's kind of band, am I right? Yeah, so it's band pass filtering. Usually, yeah, usually you will find this one is very weird. Yeah, because when we talk about the signal, we like talk about the signal is just from here, and this signal is from here. We just talk about this side. We seldomly talk about this side, but you need to know. Usually, it will have this side, but do you know why we remove this side, the left side? Do you know why? Do you know why? Actually, it's very easy to answer because if you notice that, if you observe that, you will find that this part and this part actually it's the same thing. Yeah, if you analyze this part, which means this part will apply the same thing. We don't need to talk about both. This one will have the same rule, same thing apply with this part. That makes sense to you? Yeah, you can see this part have this rule and this part will have the same rule. That makes sense to you? Yeah, that's the reason why we usually focus on this part. And then you can see if you just focus on this part, yeah, I think this one will be common for you to see. Yeah, this is just a low pass filter because just remember here, this x-axis will not be t. It's not like a time. It's omega. Or what does that mean? It will frequency. That makes sense to you? Yeah, which means your like frequency only because this is coefficient, am I right? If you multiple a coefficient to some specific frequency, only this part has a value. Otherwise, it will be 0. That makes sense to you? Yeah. So this is a low pass filter, and this is high pass filter. Why? Because for the low pass, low frequency, it is 0. Am I right? So which means you multiple. This is just the coefficient, am I right? You multiple it to the specific frequency, which means you just remove it. That makes sense to you? So we call it a high pass filter. This is band pass because this one, here is 0, here is 0. Only this one has a value. And this is band stop, which means only here is 0. Otherwise, it will be pass. That makes sense to you? Any question? Okay. And then let's talk about some examples. Actually, this examples is just we talk about the very often used FT pairs. Yeah, the first one is if we have find those two signals FT. Yeah. Do you have any clues? Yeah, here we usually try to if I speak FT, which means FT coefficient, I just remove it. Yeah, just simplify that. Yeah, which means we need to use this equation. I'm right. Yeah, if we don't have clue, we always use the equation we talk about. Yeah, so which means yeah we want to use this equation. I'm right. Yeah, so this is just I put the x1t here, and then you will find. Yeah, this equation, yeah. And then this one, yeah, we know, we learned this. We learned this before. Actually, here, we just, you know what's property we use here? Do you know? what property we use here? Yeah? Actually, what property? Yeah, this is a tricky one. What property we learned before? We learned shifting property, right? If it is a shifting property, yeah, it is a shifting property. If it is a shifting property, which means maybe you will have t minus t now or blah blah blah, and right? You will have this one, but for now you have x t now. Yeah, actually it use very important. Yeah, actually this property we learned it in the chapter 1 called sampling property. Do you remember? Yes, which means for example, your xt is any t, this is t, this is xt, and your xt is just any signal. Yeah, here, and the delta t minus t naught, what does it mean? Delta t minus t naught, what does it mean? E delta e minus t naught. What does it mean? Which means when t equal t naught, it will be 1. Otherwise, it will be 0. Am I right? Yeah. For example, our t naught is here, which means you have this one. Am I right? And did you notice it is multiple? Am I right? This one multiple this one. What does that mean? You only have here t naught here, this value. That makes sense to you? So which means when xt multiple delta t minus t naught, you only have xt naught value. That makes sense to you? Yeah. And you will have a question. Oh, here then our equation will become x t naught like d dt, right? And why this one equal? Oh, sorry, equal x t naught. Do you know why? Yeah, this is the other tricky one. Yeah, because xt naught actually is not a function. Am I right? It's a specific value. That makes sense to you? Which means no matter how your t change, this value will not. It's just this one value. That makes sense to you? Which means it's just for example, it is 1 or 2 dt. It's just equal this one. That makes sense to you? Yeah, it will equal 2. That makes sense to you? I don't know. The no, I don't think it is 2t.
For example, you do like the integral of dx divided by x, the integral of 2 dx.
Oh yeah, I know. I got what you your point. Yeah. Let me see. xt now. xt now like oh okay. Oh yeah. Sorry. I think it's a different thing. Yeah. Which means yeah, you're right. Yeah, it's a different thing. Yeah, because if here it is the negative infinity to dt, yeah, it will like it will be 2t. Yeah, and from negative with positive infinity to negative infinity. Yeah, you are right. But here, this is xt now, am I right? And this one is dt, am I right? Which means the t naught, we don't know the t naught. Am I right? That makes sense to you? So which means it will like reverse from infinity to the I don't know how to speak it. Yeah, the xt now, since we don't know the xt now is the other function. It's just like xy. Am I right? Or xm. Yeah. Yeah, you can talk about this xm. Yeah, this is a function related to m, not t. For example, infinity y, yeah, y dt. Yeah, this is the right one. Yeah, since this one doesn't relate to t, so you just put y outside dimension. Am I right? So it will not relate to dt. Yeah, so which means this one can be put it out. Yeah, xt now, and negative infinity to dt like that. 的没分区。
T,
Let me see. Yeah. For now it will be yeah, it will be xt now and multiple t from negative infinity to the positive infinity to the negative infinity, right? Yeah. So which means yeah, this is weird. It should if we calculate by this one should be infinite, right? Yeah. Xt. Let me check again, since if there are steps, if I miss some steps, xt. xt. dt. Okay. Let me. Okay, I think you're right. Yeah, since this one can be put out, then this one should from t, and this should be t. And t. Yeah, it should be 2t multiple xt0. 2t. Okay. Yeah, let me check it after this. Yeah, I think this is a little weird. Yeah, let me check it. Yeah, let me check it, and let's continue firstly. This one, yeah, we know like this must right, I'm right, because we just put use this equation and put this one here, all right, and then we okay, and yeah. Yeah, t equals 0. Okay, let's try to. Yeah, because this one, then, which means this one will equal t now. Okay. I think we need to figure this out. Let's try. Let's try to. Let's try to. Let's try. Oh. Okay. I think I know that. Okay. Sorry. Yeah. Yeah, I think I just missed something. Sorry. Yeah, this is the ST, right? And this is the. t like delta t t naught, am I right? Delta t minus t naught, am I right? For now, our equation is from negative to from negative infinity to positive infinity at t delta t minus t naught dt, am I right? Yeah, am I right? This is our equation, am I right? Yeah, which means here we need to go through t from negative infinity to the positive infinity, and then multiply them together, multiply and add them together. This is I, am I right? So which means this one should equal like x negative infinity delta negative infinity minus t naught plus x negative infinity plus 1 multiple blah 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 plus blah 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 blah. That makes sense to you? Yeah, let me write it clearly. You will know that. Yeah, I know what's the point. Yeah, so yeah, this is this is t, this is t now, this is delta t negative t now, am I right? Yeah, since our equation here is negative infinity to positive x t delta t minus t now dt, am I right? Which means we need to like go through all the t, am I right? From positive negative infinity to the positive infinity, and multiply them multiply those two items and add them together because this is I. That makes sense to you? Yeah, the t is just like every t, am I right? Which means this equation will become x negative infinity multiple, because t will goes from negative infinity, am I right? Which means this is negative infinity minus t now plus, because this is plus, am I right? Integral, am I right? Yeah, which means x negative infinity plus 1 or plus dt, yeah, dt. Yeah, so the very small tiny thing, am I right? And then multiple delta negative infinity plus dt minus t naught, am I right? And then plus x0 delta 0 negative plus blah 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 plus x positive infinity blah 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 blah. That makes sense. This equation equal this equation. That makes sense to you? Yeah, but we know for this one only when this part equal t naught, it will equal 1. Am I right? Otherwise it will equal 0. We know that, am I right? So which means this atom is 0. That makes sense to you? This atom is 0. That makes sense to you? Only when here is t naught, it has value. And this part is 1. That makes sense to you? Yeah, so that's the reason why this is equal at t naught. That makes sense to you? Yeah, that makes sense to you? Yeah, I think this, this one will make the most reason. Am I right? Yeah, okay. And then for this one, because t now, what's t now here? What's t now? T now, what does that mean? Which means t minus t now equals 0, am I right? Here, actual t now is what? 0. Am I right? That makes sense to you? Yeah, which means t now is 0, which means this is you need to equal eg omega 0, am I right? Yeah, so it equals this one. That makes sense to you? Yeah, it will equal 1 because e power 0 will be 1. That makes sense to you? Yeah, this is just when your signal is delta t and your ft will equal 1. And then let's check the other one. For this one, what's the t now? T now is t now, am I right? And then, which means your like result will be this one, and then you will have this one, am I right? So which means when your signal is delta t minus t now, and your ft coefficient will equal this one, or ft, am I right? That makes sense to you? Yeah. This is the example, yeah. Yeah, what's the relationship? What's the relationship between x1 and x2? You know, do you like did you notice? What's the relationship between? Yeah, that's right. Yeah, it is shift. But here you need to pay attention one thing. Don't be confused with this one. Yeah, because here you can see the omega is now omega now. Omega now is fundamental frequency, right? Fundamental frequency only related to the periodic signal. This omega, which means it's frequency, it will variable, right? It's a function. That makes sense to you. It will be shift, but now now similar like fs. Yeah, you need to pay attention to that. That makes sense to you. Okay, and then let's try to review the other one. If let's find the inverse ft of the following. Yeah, this one. What are the inverse? Which means I give you ft coefficient, let you to represent the signal. Yeah, what equation you will use? Synthesis. Synthesis, this one, all right? Yeah, also like we have this equation. Yeah, this equation is just similar with the equation we just talked about that. And then you can see for the first one, if you're like x1, your ft is 2 pi delta omega, and then you just use this equation, put the x1 j omega here, and then you will have this one, and then you can see, because this is this will equal 2 pi omega now, right? And oh yeah, here omega now is what? Is 0, am I right? The omega will be omega now is 0, am I right? Omega is 0, which means 2 pi of 0, am I right? Yeah. Then this will be 1, and this will be 2. Here is a 2 pi, here is a 2 pi. It will be 1. That makes sense to you? Any question? Yeah, because you can see. Yeah, which means for this one, because the x j omega is 2 pi delta omega, which means the omega now is 0. I'm right. Yeah. So this is just 0, 1. Yeah, 0, 1, and then this part is 2 pi omega 0, and it will be 2 pi. And here is a 2 pi. Yeah. It will be 1. Yeah. Okay. And then, sorry. Yeah. Okay. And let's check the second one. Yeah, we also use this equation and the second one, which means what is omega now here? It will be 2 pi. Am I right? Yeah. So which means, yeah, because here your it will be x omega now. Am I right? So let me check. Oh, yeah. Because this is the like order thing. Yeah, because this part, just delta omega minus 2 pi, and this part should be put here. That makes sense to you? Yeah, so here the x omega is 2 pi e g omega t. All right? That makes sense to you? Yeah. You just put it behind. Put this like front, and this whole part is just that this equations 2 x omega. Am I right? Yeah, and this part is just this part. That makes sense to you? And then this is x omega now, which means omega now is 2 pi, which means here we keep it, and here we just put 2 pi here. Am I right? Yeah, and then 2 pi, and this 2 pi will remove, and then we will left this one, but omega will be 2 pi. That makes sense to you? Yeah, any question? Okay, and then the third one, yeah, it's a similar thing, but here the omega now is negative 2 pi. Am I right? Yeah, because here, yeah, the omega now here is negative 2 pi. Because the negative 2 pi is a positive 2 pi. Am I right? Yeah, so it will equal this one. Yeah, this is just like the signal. Am I right? Yeah. So you can see from those three different problems, you can see if you in your first domain, if you have this signal, all right, the FT is similar like this signal, and in the time domain, you will have this kind of signal, all right? Yeah, actually you can see here why the first one is just a 1, because omega now here is 0, all right? When it is 0, it will be 1, all right? So you can see when your like fluence domain FT similar like this, and your time domain signals will like this. That makes sense? Yeah. Okay. Then let's talk about the periodic signals of FT. You can see we know like if your like FT looks like that, and your signal is this one, is similar like this one. That makes sense? Yeah, we just talk about that. All right. And which means if you multiple AK in this equation, and then you will have AK here. Do you know why? Yeah, actually, we always talk about the LIT system. Yeah, so when you multiple one atom, you will like for the signals, you will have this one. Also multiple this one. Yeah, let me give you. Yeah, because for LIT system, you can see if you have like a AY, and then your actually it's opposite, and your signal is like X. And if you A1 X1, if you have Y2, and your signal is X2, yeah, sorry. Yeah, if you have a Y1, like the corresponding is X1, Y2 is corresponding as X2, and then AY1 will corresponding with AX1, BY2 will corresponding with BX2. If you have AY1 plus BY2, and that corresponding is AX1 plus B X2. Yeah, this is LIT system, LIT, yeah. So yeah, we will have this one. And then you can see if a periodic signal with frequency omega now and Fn as coefficient x xt, Fs coefficient is AK. Yeah, and then you can see we know like this is the Fs synthesis equation, am I right? It's equal to this one. That makes sense. Yeah, we learned that. And then, yeah, we will have this one. Yeah, that's G will equal this one. Yeah, which means, did you notice? Do you know why? You can see when you compare this one to this one. Did you notice this one and this one? It's the same thing. Yeah, which means if you also the LIT, if you add all this together, which means you add this part together. That makes sense to you? Yeah, which means you add this part together. This 2 pi because it's not related to cat, so it will be output. That makes sense to you? Any question? Yeah, this is just the periodic symbol. How should the FT of periodic symbol? Let's use this equation to represent it. Yeah, any question? Yeah, we will like mainly focus on this FT and periodic signals in next class. Yeah, I will talk about some examples. Okay. Yeah. Any questions so far? Okay. Yeah. Let's